Everybody outside, feel free to chime in if you can hear us or not, as always.
All right, so I think since we have a lot of stuff to cover today, I might just only spend a few minutes to do this intro. So what I'm going to do is first do a quick review on the creating models and then talk about this paper. The idea of this paper is basically to try to help ecologists to avoid a simple mistake that people make in analysis. So,
Yeah.
So the creating model, so the first equation we see is basically how we define a creating model. So yi is a just random, spatial random variable with a constant mean mu, and zi is a zero mean and spatially correlated error. And then epsilon, which is independent error. So we often express creating model in terms of semi-variogram, which models the variance of difference between variables, as we can see the first equation in the semi-variable. That's how we define a semi-variable mathematically. In the next function, the next equation, gamma m dij, it's basically a general like function, a general like semi-variable function. Where the rho m it's a autocorrelation model. If you see the right in the slides, those are the autocorrelation function models where we have, like, for example, exponential function, Gaussian function.
So like you're saying that rho sub e d I j, the first row on the right hand column,
Yeah.
that's an exponential
That,
function.
yeah.
And which are the other ones?
And I think it's indicated by the subscript, like e is exponential, can rule with s.
Yeah. So S is probably spherical.
Yeah, right, and G is Gaussian. So the last equation under the semi-variogram column is the empirical semi-variogram function, which is a unbiased estimator, has many good estimation properties. As if you substitute the Kriging model, you can see the mu cancel out, so, which is pretty good. You don't have to estimate mean. So, and then we can also express the Kriging model in terms of covariance matrix. As you can see in the middle column, well, the capital C is just a covariance matrix, which is just a scaled correlation matrix. Then, if you want to include the nugget effect, which is the sigma 0 or sigma O squared, and multiplied by identity matrix, and then the overall variance is just sigma p squared plus O squared. So if we plot the semi-variogram and covariance matrix, let's have the X slide, please. So if we plot it out, they look like this. So auto covariance, as we can see, it's decreased as we increase the distance. And semi-variance, which basically just model the similarities. No, the models are different. So so we can see as the distance increase, the semi-variable increase as well. And alpha, it's a range parameter which basically controls how quickly the autocorrelation decreases as the distance increases. So can you go back to the previous slide?
Okay.
So if the distance in this autocorrelation functions is Euclidean distance, then the covariance matrix is guaranteed to be positive definite, which is very important because requiring a covariance matrix to be positive definite is the matrix analog of requiring a variance parameter to be positive. So a lot of times we see the error message saying the Hessian matrix is not positive definite, and then so it's not invertible. But it doesn't really mean that the matrix is not invertible because for non-positive definite matrix, the inverse may still exist, but if a Hessian matrix is not positive definite, then the covariance matrix is not positive definite. So the software just doesn't even bother to check its singularity. So a lot of cases, there are examples when people are using non-Euclidean distance in these correlation functions, which might cause a problem potentially because the covariance matrix is not guaranteed to be positive definite. So the authors provide a few examples as in yes, slides. Yeah. So the authors provide a few examples showing, as we can see, figure A, for example, you have a circle, and then there are several points on a circle. So the distance here is defined as the shortest path between 2 points, which is not Euclidean distance. And then if you look at the minimum eigenvalues, as we increase the range parameters, the eigenvalues can be negative. And also two other examples on here. And then also reanalyze a data using a published paper, and he found that actually a lot of cases that you get a non-positive definite covariance matrix. And he proposed a method which is reduced rank methods to deal with this situation. Well, I'm not going to go details into this one, but if you are interested, take a look at the paper.
Well, so that's a lot to cover. What would people say are the kind of take homes from this?
You have to be careful applying spatial theory to non-Euclidean spaces.
Yeah, and what happens if you do it wrong? What's the?
Non-positive definite Hessian matrix.
Yeah, you get, or the covariance matrix is not positive definite, and so you end up with sort of an uninterpretable, random set of random effects. I kind of like this figure, this paper's plot of just the autocovariance and the autocorrelation function and the semivariance. We haven't really talked about these yet, and we're probably not going to talk about them too extensively. In the class, we're just going to talk really about autocorrelation functions and autocovariance functions. But if people, Jay defined it kind of quickly, but has anybody seen a semivariance function defined before?
What exactly does it mean? Semivariance?
Yeah, so
Sort of broadly.
totally. Yeah, so it's an old way of computing a covariant the covariance between different location data at different locations was to do this empirical semivariance function, which is the bottom left equation here. And so what this is saying is you would take data y at one data y, y sub I, and another data y sub j, and look at the difference between those two data, the difference squared, and then you would take the average of those squared differences for a given bin, defined as the given distance between those two data points. And so you'd end up with sort of the average difference between data at 0 to 50 meters, or 50 to 100 meters, or 100 to 150 meters. And if you plot that out, that average variance is a function of distance. And divide it by 2, you get the empirical semivariance, and then people would fit a curve through that. And that was sort of the one way that people kind of derive spatial models. So on this top right panel where we have semivariance, that means that it's semi because it's divided by 2, and the variance because it's the square difference between data on average for a given distance on the x-axis. So, if you're at really small distances, because they share, the spatial term, because they're not that distant, their spatial term is likely to be similar, and so that square difference is lower, the y-axis is lower at low distances on the left-hand side than as distances get greater. Anyway, and I kind of like this plot because it shows the shape of all these different semi-variance functions that people have ever really talked about. And I have no idea why you would really want to use a Hole effect, the oscillating one,
Yeah.
But
What is the Hole effect?
I have no idea.
Okay.
It's just another model.
Okay.
Yeah.
You could use a Matern or an exponential covariance.
Mhm.
So these are directly convertible between the two. You can think of a variogram function as the opposite, sort of the opposite of a covariance function.
Okay.
Because if you take that maximum, they call it the CIL, so 3 there is the maximum variance. Basically, if 2 points are far enough apart that they're independent, then their variance between each other is going to be about 3. So if you flip that over,
You mean, and I think, John, you probably mean like the asymptote of all of the
Yes,
lines
exactly.
on the top right.
Yeah.
is 3.
So the
That's
spherical
the-
actually goes to 3 there, but the other ones sort of asymptotically approach it.
Yeah.
That's called the CIL.
Mhm.
So if you do 3 minus that function, you get the covariance function.
Okay.
And that's because if they're independent, they essentially have 0 covariance.
Mhm.
And that's, if you thought of it on the correlation scale, you could scale your semivariance sort of similarly. You imagine you would go from a correlation of 1 at 0 distance to a correlation of 0 at 2 for the spherical, or sort of eventually asymptotically for the other ones.
Yeah.
If that helps.
Yeah, I mean,
Yeah, it does. Thank you.
so this terminology, CIL, like if people heard these terms before, CIL, nugget, and range, is anybody willing to kind of try to define them for us quickly here?
Nugget's the kind of variance when you're at 0 distance. CIL is the asymptote. The range is kind of when it hits that asymptote from 0 to, or the distance. Right?
Yeah. And this sort of, there's this whole vocabulary of CIL and nugget and range, semivariance, that I guess I associate with sort of the geostatistics and sort of Kriging and this sort of group that, one group of people that kind of, did a lot of research into spatiotemporal models. And so because that's historically a lot of the terminology people still use those terms. But we're doing all of these models kind of as a hierarchical model, and so I guess my presentation is mainly without using those terms and just deriving things from covariance matrices, which is why we haven't used those terms much, and probably won't use them too much in the future. But I'm glad, thank you, Jay, for doing this paper, because it's good to kind of talk, see, like Jay, I think the author of this, Jay Verhoef, I think got, cut his teeth with geostatistical models. So he's the kind of person who's likely to use this terminology more. Anything more we want to talk about with this? Okay, and then I'm pretty sick, actually, so I think I got sick on my trip, so I'm curious to see how far I'll get before I just kind of pass out. But and then, of course, thanks everyone for being willing to cancel the class on Tuesday. Jay and I miscommunicated about I miscommunicated about needing some help. So anyway, so this week is all about looking at different covariance matrices, and so we'll start out with sort of trying to think about Cholesky versus eigen decompositions and how you can do those to interpret a covariance matrix or generate a covariance matrix, and then also covariance functions as an alternative way to generate an admissible covariance function, like we started talking about already. Okay, so last week we were talking about linear and nonlinear time certain state space models, and you could think about the next step for that is to start stacking time series from multiple species and trying to interpret things about them. Let's see, I'm trying to remember what I was focused on here. So, the questions I imagine that a person might want to have. Well, okay, how about this? So, what are some examples of sort of time series that you might have might want to analyze jointly and might want to learn something about their kind of joint dynamics?
Number of births and deaths.
Totally. Yeah, so exactly. So you could have a single population and you might have a time series of births, and this is what you're saying, and a time series of deaths. And you might imagine that like good years, the number of births goes up and the number of deaths go down, or you could imagine, maybe temperature, like some plankton, I think, like, the number of births goes up with temperature and the number of deaths also goes up with temperature. And so you could try to figure out like what's the correlation between births and death rates in a population. Any other kind of stuff that, examples that people have?
Amount of publications that staff submits and the amount of daylight in the day.
And what do you hypothesize about? I'm always curious about this.
I was wondering about that too. I wanted to look at take the SAS publications and look at the days submitted. And
Yeah.
compare it versus the time of year.
Totally.
But
I'm definitely a winter publisher.
Oh, I'm guessing that everyone starts pushing it out summer.
That's funny.
Really?
I think I'm opposite. Yeah.
Yeah, I am too.
In the summer, I'm like hiking. I'm not gonna.
I'd rather be outside in the summer, yeah.
But everyone gets depressed during the winter, so
Yeah.
productivity goes down.
Yeah, maybe. Yeah. Yeah, I mean, well, right, or another one is just publications for different people. I would think my, I'm more likely to publish when I'm depressed, because then that's when I actually can focus on work. So my publish when depressed brethren are probably anti-correlated with Grant's sort of work hard when it's summer and you're awake. Okay. Another one that came up in last class, but I don't think anybody here is focused on, is sort of positional data. So, you could imagine that you've got you've got seabirds that are tagged and they have some positional location like eastings and northings, and, that position will change as some random walk or, Gaupert's model if they have a home range or whatever, an autoregressive process. And if you've got 30 tagged birds, you might want to jointly analyze them to figure out, if they all have the same home range, if they all have the same variance representing the variance of their, colonies, home range size, whatever.
Like the Wolverine quantitative seminar we had.
Yeah, well, right.
Weeks ago. Yeah.
Totally. Yeah, so one way, he took it, sort of a different direction, I think, but there's a lot of different ways to sort of stack data from multiple individuals. And one of them is this sort of multivariate time series model. We'll also start getting into forecasting future changes in the lab. And so this, I actually don't know, strictly speaking, if or when it's admissible to have a covariance matrix that's semi-definite rather than. So does anybody know sort of the difference between positive definite and positive semi-definite matrices?
Can't you not have zeros in positive definite?
Correct. Yeah. Whereas positive semi-definite, you have some of the eigenvalues could be are zero. So a positive definite matrix is one where the eigenvalues are all greater than 0. And a positive semi-definite is where they're all greater or equal to 0. And leaving out whether, you know, a covariance matrix certainly can't have any negative eigenvalues. We'll see some cases where it's useful to think about a covariance matrix that has a 0 eigenvalue, but I don't know if that's strictly the way that people want to talk about it or not.
Isn't it not invertible if it does have a 0 though?
Well, exactly. So you certainly don't want a Hessian matrix. Anything you have to invert, you don't want to have. You don't want to have a positive semi-definite.
Mhm.
So, and that's because, you know, to invert a matrix, you need to calculate the determinant. And the determinant is the product of all of the eigenvalues. And so if you've got any of your eigenvalues is 0, the determinant is 0, and then you've got to divide by 0, and it doesn't make sense. But there are cases where you can assemble, we'll see it in a bit, there are cases where you can generate a process that has a 0 eigenvalue without actually inverting it. Again, I guess this is something we, you know, if somebody, I'd love it if somebody looks it up and it helps me solve if I'm supposed to be talking about positive semi-definite or strictly positive definite covariance matrices, but.
Covariance matrices can be positive semi-definite.
Okay.
And you get, so the simple example I've run into is if you have 2 observations at the same location.
Yeah, with no nugget.
With no nugget, then you're going to have 2 columns that are exactly the same. I think. Yeah, so they're going to be linearly dependent, and you're going to have a 0 eigenvalue.
Yeah.
And the other common one is like the intrinsic car model.
Sure. Okay.
Yeah, and usually they use they enforce like the sum to 0 constraint kind of thing, so that they can basically bring it back to full rank by dropping one of the columns and rows.
Well, anyway, I don't want to get too far down this rabbit hole, but so we'll stick with my definition that it has to be positive semi-definite. A covariance matrix is always symmetric, and because it's symmetric, it's easy to see that the number of degrees of freedom of it is less than the dimension squared. So in fact that the number of degrees of freedom of a covariance matrix is that p times p plus 1 over 2. So it's just the number of, which is the number of elements of a covariance matrix where you exclude the upper diagonal, the upper portion of the matrix. And if you've got 2 covariance matrices, their sum is always admissible. So that'll end up being important to us. We'll want to generate covariance matrices. Basically what we'll want to do is we'll want to have sort of a toolbox of ways of generating a covariance matrix that's admissible, by which I mean one that has positive semi-definite eigenvalues. And if we can generate a couple of those, we have a whole universe of different covariances we can generate by adding them together. So that's sort of the trick that people do to make more complicated covariance matrices out of some elementary covariance matrices that we know we can use. And this gets into, so another of these people that sort of did, arguably Fisher, but also like Searle and other people derived hierarchical models as a way of doing variance partitioning. And so once you have an additive covariance matrix, you can start saying, is sigma 1 more important than sigma 2? If you have multiple covariance matrices and estimate parameters of them, you can say, 70% of the covariance is due to some spatial effect, and 30% is due to the nugget, or another 20% is due to some network process.
So you have to a priori specify or partition variance to make it identifiable, or?
No, you can, if you have, so if in this case, say we have sigma that's some spatial process, say.
Yeah.
And we've got one admissible component, sigma 1, that's due to like Euclidean distance exponential function. And then the second one is, some network effect, like due to stream distance, non-Euclidean distance that we also know is admissible. If we have parameters that we're estimating in both of them, we can see kind of given the parameters how much they explain.
So to test, maybe that's what you're getting to next, which one explains more variance in the data set? Is that where you're going? Or?
Yeah, totally. That's what I'm trying to say.
I can ask more about it then.
Well, you want to ask now?
I was just curious if you would do something like a principal component analysis and then weight your covariances based on that?
So I'm not sure I'm following. You could do something kind of like a PCA within a hierarchical model. But I guess I'm not sure. I mean, it sounds like that's just like one form of variance. Are you? Let's talk later. Yeah, that's fine.
I'm gonna think about it.
Yeah. Like one that I tried getting into this paper, it never went anywhere because it's way too complicated. So we had distribution for 60 rockfishes, and I wanted to know, is the distribution more similar for rockfishes that have similar trait? Like, let's say like large-bodied rockfishes are typically deeper, and so they have correlated spatial distribution due to a trait. Or I could say, maybe phylogeny, like evolutionarily, like some clade rockfishes evolved to be shallow or deep. And so I ended up with decomposing the covariance in the spatial process into an evolutionary effect and a trait effect and a residual effect. And I wanted to ask, like, how much of the portion, how much of the variance in rockfish distribution is due to each of those terms. I'm kind of being hand-wavy about how this works, but that's the type of question I think you can answer with an additive covariance matrix. So there's two main ways that, and we've already started talking about eigendecompositions. I think there's two main ways that I ever talk about a covariance matrix. One of them is this eigendecomposition. So the eigendecomposition of a covariance matrix, let's see. I only ever do it for a covariance matrix. I forget what happens if you take an eigendecomposition of a non-symmetric matrix. I'm going to skip that for now. I don't know what happens. But an eigendecomposition of a covariance matrix yields a matrix of eigenvectors and a vector of eigenvalues. Each of the eigenvectors is orthogonal to every other vector, which means that the inner product, the vector product of every eigenvector is 0. And every eigenvector is defined to have a length of 1, such that the eigenvalue corresponding to an eigenvector represents sort of the portion of variance that's explained along a certain axis. So it's sort of a way of decomposing a covariance matrix into a bunch of orthogonal components and saying, out of the variance of, out of the total variance that's due to this covariance matrix, a certain portion is associated with one orthogonal component, a certain portion is due to, associated with another axis, and so forth. If Nat was here, we could talk about the sort of like ellipse, like if you've got a 2x2 covariance matrix. Let's see. If you've got an ellipse, almost. If you've got an ellipse, in a 2x2 ellipse, then the covariance matrix is a 2x2 matrix. The covariance matrix representing this ellipse is a 2x2 matrix, and the eigendecomposition would say that there's one orthogonal component. It's this direction, and then another orthogonal component this direction. And so let's see, anybody, I mean, other properties of an eigendecomposition that people know offhand? There's some others. I mean, there's a huge list. If you Wikipedia, there's a zillion different, ways of interpreting an eigendecomposition. There's sort of at least one other that sort of matters to us. Well, we can come back to it later. So, and again, as Jay's summary of Jay Verhoef's paper talked about, you end up, if you have a non-Euclidean distance, like if you rotate your study design in weird ways, you can end up with inadmissible covariance matrices where some of the eigenvalues are negative. And that's sort of the bottom line of why we have to care about this sort of eigendecomposition way of thinking about covariance matrices. And then the other way that we'll talk a lot about is a Cholesky decomposition. So the Cholesky decomposition is an operator you can do on a matrix that yields a lower triangular matrix. So if you've got a covariance matrix sigma and you do that, like, we can just do this really quickly. Well, we'll see in the lab in a second. We can do the Chol function in R, and technically R, unlike everybody else, yields a, well, I'm trying to think. R ends up doing the opposite of every other software.
R gets you upper.
Yeah, which is super annoying. Sigma. So I'm just gonna 2.7, 0.2, 0.2, 0.7. So if we've got a sigma matrix this, and we do the Chol if we do the Cholesky, yeah, we get an upper triangular matrix, whereas everybody else thinks of a Cholesky as being lower triangle. So you just have to kind of keep that in mind when you're reading about a Cholesky decomposition. I'm going to follow the notation that it's a lower triangle matrix, like most people do. So this Cholesky decomposition is useful. Well, we'll see in a bit. I mean, the main use that I see is that you can generate a covariance matrix by plugging in values for the Cholesky. You can have a set of parameters that represents the Cholesky decomposition of a matrix, and then multiply that by its transpose to get the covariance matrix that it would have generated it. So, for instance, if you want to have a 6x6 covariance matrix, well, let's just try to do a thought experiment. So, can people think of other ways to generate a 6x6 covariance matrix with a set of parameters? Like, say you want to have a vector of parameters to estimate, and you want to assemble a covariance matrix from those parameters. Do people have ideas about how to do that? The way I always do is with the Cholesky.
Okay, you can do the same. You can use these same 6 parameters and just make sure that the upper triangle is 2, 5, and 3.
Yeah, although the downside of that is that you could easily have a covariance matrix that's greater than, so like sigma 2 here needs to be less than the product of sigma 1 and sigma 4.
Yeah. So
You'd have to
strain that or hope.
Exactly. Yeah, I think that the other main way to do it would probably be to take some of the parameters and use them to make the diagonal, and then some of the parameters and constrain them to be correlations or something,
Yeah. You probably-
and then assemble a covariance matrix from this like correlation matrix and diagonal covariances.
Yeah.
And I just think that's kind of more complicated to talk about. I don't know.
Or you choose a function.
Yeah, or you constrain it to be some parametric thing. Yeah. Okay, so as we were already talking about, you can do these additive covariance matrices. So, for instance, here we've got an additive covariance matrix where the first term is an indemnity matrix times something, and then the second term is a matrix of ones times another thing. And if you do the math on this, you can just see that you get the lower matrix down here, which is just a, I forget why I did it that way. But I guess this is another example of why the additive property matters or is useful. And then, in the simulations we do, we're going to want to generate data from a multivariate normal. And of course, you can just use R functions like R MV norm. But I'm assuming that, it'd be nice for people to know a little bit more about how that's happening. One way to do this is this, using the Cholesky decomposition again. So if you've got epsilon that's a vector drawn from a multivariate normal distribution with mean 0 and some covariance, then that's equivalent to taking the covariance out and multiplying by essentially the square root of that covariance. So the Cholesky is sort of one way of thinking about the square root of a covariance matrix.
Is that parameterization faster or something? That's the advantage of using Cholesky?
Yeah, it's faster sometimes. It's faster. It's not, if you were going to generate just a bunch of vectors, random vectors, it's not any faster. But there are times when your code will be a lot faster using this parameterization because you can use it to make your code separable, like we started talking about. And we'll get more into separability next week, really. Yeah, we're gonna see, we'll see on the TMB side that this is one way that we can code up the C++ side. And the reason that that's useful is we don't have to code up the multivariate normal density function on the C++ side. I'm sorry, I'm just still thinking about your question. Yeah, just to take it one step further. So if you want to do the multivariate normal probability density function, you have to invert the covariance matrix. And that claim you can Wikipedia to confirm. But that matrix inverse is what makes the multivariate normal density function so expensive to compute. Whereas this one, the Cholesky doesn't require inverting the matrix, and so it's usually a more efficient computationally to do it. There are cases where this is more computationally efficient than doing the multivariate normal density function. Does that make sense?
I think so.
Okay, so this is just generated from this additive covariance function. I forget why I used this particular additive covariance function, but I think it was just to show the principle. And just feeding it into the existing sort of Kalman filter stuff that we've been doing, state space modeling stuff we've been doing, where, in week 3, x of t plus 1 and x of t were both scalars, and now x of t plus 1 and x of t are both vectors, which is why it's this bold font now. And that's where the multivariate time series part comes in. So this week 4 was the only one where I didn't have any C++ code to estimate anything. But it's just showing how to compute this stuff in R. So here's an additive covariance matrix for 6 populations, and it's admissible because all of the eigen, if we do the eigen decomposition using the R function eigen, all of the eigen values are all positive. And if we generate the Cholesky and do a bunch of independent normal draws, so delta IP are all independent normals, where this is the sample covariance and all of the off diagonals are basically 0 and the diagonals are all 1. So this is a bunch of unit normal random draws. And so if you take those random draws and multiply them by the Cholesky, you get something that has the sample covariance that we want. So that's the demo of how you can generate sampling, data with a given covariance using the Cholesky, as the product of the Cholesky decomposition and a bunch of standard normal draws. Does anybody want to go through that more slowly? That's just doing just confirming that this formula works, essentially. And then this, and then we've got code to simulate, a spatial, not a spatial, I'm sorry, this multivariate time series dynamics. Similar to what we saw before. So does anybody want to talk about that stuff more, or? Well, I'll take it. There's just three slides left for the lecture. So, and then finally, the other way to generate a covariance matrix that's admissible is to look up sort of an admissible covariance function, like a parametric function that generates an admissible covariance matrix, and just plug that in. So, like Jay's paper that we talked about, there's the Hole effect and the Cauchy and the Matern and the spherical and the exponential and the Gaussian covariance functions are the ones that people typically talk about. And so you can generate a covariance matrix using those, given that you have a Euclidean distance, and whatever you do is guaranteed to be an admissible covariance. So, clearly this is sort of a bridge from this multivariate time series stuff to a spatial model. So if you've got a coastline where you have, I guess, 8 different sampling locations denoted with the blue dots along this brown coastline, like south of the California Bight, in the California Bight, then you might define the correlation between samples at these locations as following some spatial function using covariance function V, and using notation S1 and S2 for space. S we'll use for space and T for time, given the distance D between location S1 and S2. So like we already saw, I think the only ones I'm probably going to talk about in the class are the Matern function and the exponential function, the Gaussian function. And so the exponential function looks like this. The Gaussian function looks like this. But there's other ones. So like in the exponential function that's listed here, what are the parameters of that function? And what's sort of the data?
You have the variance,
Yeah, sigma squared is a parameter.
and then you have K, which is the CIL.
So yeah, kappa's controlling the range.
Yeah.
Yeah. And the CIL, let's see, the CIL. I think the CIL is just sigma squared. Yeah. And it doesn't have a nugget. You could generate a nugget from an additive covariance function, where you have a covariance function with no nugget, and then you've just got some random error associated with every observation. Yeah, and then similarly for the Gaussian function, you've got two parameters, sigma squared and kappa. And so in that case, you just generate the covariance function by calculating evaluating that variance function for every distance between locations. So the distance between location S1 and S2 is 0, and so in this case, all of the diagonal is 0. Let's see, does that make sense?
So it just goes to 1 for the sigma squared.
Yeah, exactly. Yeah, exactly. Yeah, here, sorry. Yeah, exactly. So the diagonal when you evaluate this goes to sigma squared, and then as the distance gets greater, it goes to 0. So in this case, if we number it sequentially from the kind of the northwestern location, and this being 1, and the southeastern being 8, so those are the greatest distances. So the variance between 1 and 8 would be the lowest. The covariance between 1 and 8 would be the lowest of any of the covariances.
I had a question about relating this to the last class with the Gompertz model. There was the correlation that gets estimated in there, and I understand, I guess, like the distance function in that case is like just 1+, or we're thinking it more about like a stepwise, more like a discrete distance in that model? Or
Yeah.
I guess you don't have to.
No, totally. I'm glad you're thinking about this. So that one, the Gompertz model is just a smoother across time. And in that case, where, like, eventually we're going to be doing spatiotemporal models where you've got some way of generating a covariance across space and a separate covariance across time. And in the Gompertz model, we've got just a single correlation parameter we're estimating. And I can't think of a way to kind of, I'll just claim without any demonstration that the easiest way to think of that is as an exponential covariance function that you're just evaluating for that, like you say, for just that distance of 1 every time from year to year.
Right, so you can make a covariance function for every time points relationship to the other. You just don't, it's not useful to really think about it when learning the Gompertz.
Yeah, right. Well, exactly. And there are people that do, there was a paper in ecology sometime in the last 10 years where people revisited the state space Gompertz model and did it for irregular time intervals.
Okay.
Yeah, there's probably more useful work. I won't get too far into it. If you're interested, we can dig up that paper and talk through it.
I think the question I was really more interested in is for the random walk where there's not like that correlation estimated explicitly, but presumably there is some correlation between point 1 and point 2 and point 3 and point 4. Is there a covariance function for that? There's like your...
Yeah, so in that case, so if you've got a random walk that corresponds to, in geostatistics land, you can convert a semi-variance to an auto-covariance function, but only if it's stationary. And if you've got a random walk, the semi-variance function looks like this. Sorry. It looks like just a straight line increasing with distance. This is going to be rough. Semi. Oh god.
That's good enough.
Yeah. Yeah, so the semi-variance is just of that random walk is increasing infinitely with distance. And that's another way of saying that process is not stationary. If you simulate a random walk out to infinity, where time goes to infinity, the variance also goes to infinity, which is sort of what you mean by a non-stationary process. And so, given that the semi-variance is not stationary, there's no way to convert the semi-variance to an autocorrelation function. Is that helpful? Or I'm sure there's another way we can talk about it that might be more intuitive for whatever your goal is.
No, I think that makes sense. But so you're saying that you can't, there's no like function for like to calculate a covariance based on the parameters you estimate from a random walk?
Yeah, the covariant, yeah. I mean, a random walk is the Gompertz model where that parameter rho equals 1. It's the limit of that model where rho goes to 1. And so I guess you could say that it's one where the correlation goes to 1, but
So
I don't think you'd want to say that because it just stops making sense.
I'm thinking sort of if you think about constructing the covariance matrix of a random walk, so you have each you'll have the first off diagonal, right? Because each one depends only on the one right before it. Maybe not, but you'll definitely have that. You'll have your diagonal, and those will be, 1, say, because you're choosing 1, but then it depends with correlation 1 on the one before it. So you're going to have a like at least tri-diagonal matrix where that all 3 diagonals are 1s.
Yeah, I think it's a tri-diagonal inverse, like precision
right,
matrix.
yeah, the precision matrix.
The covariance is dense.
Right, but then that's definitely singular.
Yeah, I think the point is,
model.
yeah, well, right, exactly. I think we'll get into this actually in week 5 again, where we look at 4 different parameterizations of a spatial process. And some of those are separable and non-separable, but the separable one, you have to assemble the inverse covariance matrix. And if you have the rho parameter equals 1, like a random walk, that is not invertible anymore. So you get separability at the expense of losing the ability to have a random walk process model.
Yeah, no, that makes sense.
Yeah. I think maybe another take home from this that's also hopefully clear throughout is that, yeah, there's just a lot of different ways we can talk about the same model, and some of them are more clear for one use and others are more clear for another use.
I didn't want to muddle things, I'm just thinking.
Yeah. Yeah, let's make sure to ask that question again, like week 5 or 6, if it's still of interest. Well, I'm happy that I'm not like passed out yet. So I think I'm just gonna keep going. Does anybody want a break now, or is it okay if you want a break?
Yeah.
Okay.
If that's fine.
Yeah, okay. Let's take a 5-minute break enough?
Jim, do you want a cough drop? Would that help?
Yeah. So I think I'm recording again. People offsite can still hear me, right? Okay. So using essentially the same, the same kind of squiggle plots, the question might be, how best should we forecast the next 20 years for these, these time series, whether they're, whether it's forecasting, am I gonna publish more in the winter next year, or does having Avi mean that I have some regime shift in dynamics, or whether it's, births and deaths, their covariance changing over time, or whatever it be. Yeah, so how do we estimate parameters in a multivariate process, and also how do we forecast future values given those parameters? like always, we're going to kind of go with this sort of probabilistic modeling format where we hypothesize some data generating process. We estimate parameters using maximum likelihood. We propagate uncertainty using the delta method or a generalization of it. And then we're also going to talk about the simulation, like ways to build in simulation testing into the TMD code and use that to check sort of consistency of your parameter estimates. So as we've talked about, we have this multivariate process. Well, this is a multivariate random walk process. And then we've got observations that are all normally distributed, with sigma m squared being the variance of the measurement process. So like we worked through before, if we've got this first line, and I guess partly I want to explain this because when you write a paper, you probably want to use different notation than when you actually code your model. And so it's useful to understand what are the different parameterizations that result in the same model. If you were writing a paper, you probably want to use the top line, because I think that's most informative about the data generating process. That's the one where you can see that it's a random walk process most easily. But if you're coding up this model, you probably want to code, one efficient way to code it up is that bottom line, because it replaces the multivariate normal density function, which you have to invert the covariance matrix with this Cholesky matrix that you can use. Anyway, we originally this was going to be obviously a separate Tuesday and Thursday, so this is kind of okay. So replacing what was previously this first line with two lines where we use a normal distribution for every process error and multiply it by the Cholesky matrix to get the updated equation. So the first block of code is just generating a data set, for years 1 through, well, we've got observations for years 1 through 100, and then we're simulating dynamics for the following 20 years, but we're not generating data for those years. So we've got true state x for years 1 through 120 for each of 6 different populations. And then we've got observations for years 1 through 120, and then a bunch of MAs for the following years. And to fit this in TMB, on the R side, it looks very similar. As always, we define the tag list of data, parameters, and what's a random effect. And on the C++ side, as always, there's a lot of ways you can parameterize it, but I'm defining this function R is NA. So I've actually never, I don't remember why this function is useful. It was sort of useful in an early version of TMB, and I don't know if there's a simpler is NA function. But this R is NA works the same way that is NA does in R. So this R is NA is just a function that, like 5 years ago, Casper, I posted something on GitHub to ask how to do that, and this is the function he gave me.
Can you turn the front lights off? It's easier to see.
What's that?
Can I turn the front lights off?
Oh, sure. Yeah. Yeah, so is NA, and I think we've defined user functions before, but as a reminder, you have to put the include tmb.hpp at the top, and then you can define any set of user functions you want, where the name of the function is this, and the inputs are in these parentheses, and then you just return something. And then I'm going to use that is NA later in the code.
What's as double?
I have no idea. I don't know what this. I don't know why this function is needed to do. I don't know why you can't just do this R is NA.
Wait, where do you use R as NA?
In the definition of is NA.
Oh.
Out of curiosity, what do you recommend for like these obscure C++ like operators, or functions? Where can we search what they actually mean?
Well, I mean I think like a lot of their docspin stuff is sort of indexed in sort of a weird way. Oh man. Let's see. The TMB. Wonderful, we just find our way. Yeah, so I asked back in 2014, and there's some discussion of this, and I don't know why we came to the solution that we did. Yeah, I mean, you can always go to the TMB. Well, let's see.
But on the tmb.io GitHub website.
And is that the Doxgen documentation? Or?
Yeah, a lot of the kind of more functions that the TMB functions are built on aren't well documented.
Yeah, no, it's a problem. I don't have a good. I don't know that there's any one good answer to that. I think you should just kind of have to. Yeah.
Type
Is
TMB
NA.
is NA into Google. It comes out.
I've done things like that.
Yeah.
Just like,
Yeah.
Sometimes you can
So
find
R,
it, but
yeah.
you can't. Yeah.
So I agree that if it was packaged as part of TMB, the R is NA would be searchable in this the Doxgen TMB documentation we're looking at.
yeah.
And like you say, it's not showing up here, so it's some.
Or I guess
That function apparently is some dependency that a TMB is bringing in.
Yeah, I guess what version of C++ is TMB using then?
I don't know.
Okay.
Sorry that I don't have a better answer.
No. C level.
I mean, I think that maybe one good lesson is that you should just be really careful about trying to use special functions. I mean, almost everything I do in TMB is either just basic loops, like basic arithmetic, or there's a set of macros that I use, special functions that I use in this package called density that we'll start seeing, I think, next week. So there's a bunch of special objects that you can define for spatial processes, and we'll see these all caps locked. I've been calling them. I don't think they're actually macros, but I don't know what to call them because I'm not a computer scientist. so we okay skipping that non-answer for now?
Yeah.
I think I found R is NA is from our CPP.
Okay, yeah, and it looked from the Google thing originally, it looked like that also. I didn't know that RCPP was sourced in as part of TMB, so I'm a little confused about why that would.
Yeah. I guess they're more tightly integrated.
In my experience, I think what doesn't R has like nicer random number generation than C somehow. I know when I used RCPP in the past, we had to like link to R to generate random numbers. I don't know.
Weird.
They're probably good libraries and old libraries in C for generating random numbers.
Yeah.
And R is continuously updated. Some of those C libraries are easy.
Yeah, well, I don't know too much about this. So I'll just kind of keep going through this block of code. So in this case, I'm reading in this matrix Y sub TP, and as we saw before, Y sub TP is a matrix with dimension NT by NP, and the reason that I want to use that is NA is that I want to put in an NA for any entry that's missing, any data that's missing, and so we'll try to predict the state associated with both the measurements and the data, where the years where we don't have any measurements. I then extract the dimensions of that matrix. And I think there's a bunch of ways that you could do that, but here I'm just saying, extract the first column and then calculate the length of that resulting vector. And that's the number of years. Is that what was squeaking? That's funny. And then here's the log of the measurement variance, where we use log again so that they can be anywhere from negative infinity to infinity, whereas the variance has to be positive. There's a vector of the initial state. There's L sub P that I'm defining as a matrix, but because it's L for lower, you've got sort of a hint that it's a Cholesky decomposition, or sometimes it's called a loadings matrix. And then this parameter matrix, delta sub TP, which is the set of process errors, the IID process errors. And so the covariance will be LP times its transpose, and I'm here using another function, dot transpose. And I'm not sure, I guess we might as well just start checking what's documented and what's not. So this is funny. So for instance, I didn't know that transpose is defined for an array where it just reverses all of the indexing, I guess. But in this case, it would, if you wanted to find a transpose, you go into Docgen would have succeeded in finding you that function. So that's the covariance matrix, and then I generate all of the correlated errors. So delta is the uncorrelated errors, and epsilon TP is the correlated errors. So I define that matrix of type with the right size. I initialize it to have a bunch of zeros. So unlike R, C++, when you make an object, doesn't necessarily define all of the elements of that object to be 0. And so down here, I'm gonna sum, instead of using matrix multiplication, which sometimes sometimes causes debugging errors in TMB, I'm just gonna use a loop, and the debugger will be smart enough to sort that out for me. There's not really any speed loss that I'm aware of. But I'm gonna use this plus equals, which means that it takes the initial value and adds on the part of the product of that matrix multiplication, and so I have to initialize it at 0. And then I do this loop through the matrix multiplication and calculate epsilon TP as the product of the loadings matrix and the independent errors. And then I predict the states where the first year is equal to the, I guess this set of parameters plus the first process errors, and then subsequent years are the year before plus the process errors. I then define the objective function and go through and just add, subtract off the log likelihood of the independently IID standard normal deltas, like the uncorrelated process errors, and then also the data given the states. So that's the whole block of code. So like we were talking about, we don't have to evaluate a multivariate normal density function, because instead we're defining all of our process errors as IID standard normal, and then multiplying them by the Cholesky decomposition of the covariance to yield epsilon that has the covariance that we want. Does that make any sense? Anybody? You want to talk about it more? I don't mean to.
Yeah, that'd be great.
Yeah.
So can you go back to your assumption that everything is IID again?
Yeah,
Can you
totally.
just say that part again?
Yeah. So it goes back to this claim here, that if we have a vector epsilon that has a certain covariance, we could generate this using like the DMV norm function in R with the covariance sigma and the mean 0, or we could generate a bunch of independent and identically distributed standard normals, delta, and then multiply those deltas by the loadings matrix, and that would yield an epsilon with a given covariance. And the reason for that is that, if you've got what's a good way of doing that? If you've got a covariance matrix, I don't know. Anybody have a good intuitive way of explaining why that would work? If you've got a matrix V, oh yeah.
I'm trying to understand why you can go from correlated to uncorrelated using the Cholesky.
Mm-hmm.
So one way that I've thought about it is that so if you wanted to go from a normal 5, 2, if you have some random number and you know that it's distributed as normal 5, 2.
Like mean 5 variance of 2.
Mean 5 variance of 2.
Mm-hmm.
Or variance of 4, let's say, to make it a little easier. And you want to rescale that so that it has a distribution of normal 0, 1, get your z-score, right? You would subtract 5, well, you would divide by 2, square root of variance, and subtract 5.
Okay.
Now that transformed number is going to have a normal 0, 1 distribution. So you can do the same thing with a vector. And if you think of the covariance matrix as your equivalent to your variance, you need to divide by the square root of the variance. So the Cholesky is sort of roughly equivalent to a standard deviation.
Yeah, it's one way of thinking about it.
Yeah, so you can divide, which is a matrix solve, essentially, anti-multiply, kind of. And get it to a normal, and then you subtract whatever your mean is. In this case, we're usually assuming 0, so that's not an issue. But when you do that, you're dividing, so now you have that solve basically gives you a multivariate normal where you have ones or something only on the diagonal. because you're doing the equivalent of dividing by that standard deviation. And once they're on the diagonal, it's normal, so they're independent. And now you can deal with them individually.
And sort of what we're doing is the opposite, the opposite flow of that. So we're taking a bunch of independent normals and multiplying them by the square root of the variance to get to the variance, the covariance, or target covariance.
I think you can use, there are a lot of ways to define the square root of a matrix.
Yeah.
And Cholesky happens to be one that's particularly well suited because it's more efficient than the others, and it only works for positive semi-definite matrices. So we default to the Cholesky, but you could find the square root of the matrix using the eigen decomposition or the singular value decomposition and end up in the same place.
Okay.
Yeah.
Thank you. That's super helpful. Okay. Yes.
Yeah, that's a good way of thinking about it. I mean, yeah. And like, you know, just going back to kind of elementary, you know, algebra with random variables. If you have, you know, B is a random variable A times a constant C, and you know that, you know, the variance of A equals, you know, some constant, some value, then, you know, the variance of B equals that times C squared. And so if you've got some vector, the kind of analog of this is if you've got some vector, find random vector. And here, I don't usually work with random vectors, so I don't know what notation to use, but I'm just going to use, yeah, I'll just use it. So where, if the variance of A, of the random vector A equals V, that's a stupid way of doing it, then, and if this is a matrix, then this is, let's call this L, so to make it analogous, and this is L times L transpose. So what John was saying is sort of, you can rescale, you know, one random variable to have a different variance by taking the square of the thing, you know, by multiplying by a constant squared is how it affects the variance. And yeah. If you've got a bunch of random vectors, similarly you could do, I guess it's this way. Yeah. So if this random vector A, it is a bunch of standard normals, that means that the variance of A, the covariance of A is just an identity matrix with a variance of 1 on diagonal and 0 covariance. And so that would mean that the variance of random vector B is just L times an identity matrix times the transpose of L, which would be equal to L times the transpose of L, which is, given that L is defined as a Cholesky, that means that it's the covariance sigma squared that we want. Tell me, well.
For the delta TP in the C++ code, like I just related back to that.
Yeah,
It's a matrix of essentially of 0, 1 standard normal draws, but it's modeled based on data. It's modeled based on, like, I guess where is it coming from? Like, is it interpretable given, like, say, like, that you have all of your data? What is, like, like one cell of that matrix? Is that, like, something that makes sense to me, or is it just sort of a math shortcut that can't really be interpreted?
I think it's mainly math shortcut, but
Okay.
what could be interpreted is the epsilons. So if you take the delta and multiply it by the loadings matrix, so like in the notation that we were using, I'm trying to find the right, okay, so I'll go back to lab where I definitely had it. So the point is that we want to fit the model in the first line, but we want to do it without having to evaluate a multivariate normal density function, because that multivariate normal density function has to invert the sigma sub x, and that's really costly. And so we can, each of these steps is kind of decomposing it a little bit, and I think what we're all sort of struggling with is from this block of code, the second block of code, the third block of code, where we take a multivariate normal epsilon, and this should have been, sorry, this should be a vector notation, where the epsilon is multivariate normal with variance epsilon, and we replace it with delta that's a multivariate normal with a bunch of IIDs, a standard normal draws, and then we multiply it by the Cholesky to get what was epsilon. And so in this model, I think what we want to interpret, what's interpretable is the epsilon, which is the kind of process error, and the delta is just a construct to kind of get us there.
Okay.
And that's why in the code, I record epsilon sub t p as an intermediate calculation, and we could, here I guess I saved epsilon tp, and we could compare it with the epsilon, the process errors that we use to generate the model.
P is the index of the observation at each.
Yeah, so p is my notation here for the number of time series. So like if in this case, we're generating 6 time series where each time series has 120 observations. So epsilon t sub tp is 120 by 6 matrix.
So in the beginning part of this code, you're reading in your data matrix, and then the log var m parameter is just like a single constant of variance of your matrix, right?
So that's the measurement variance, and that's why I'm calling it var m for measurement, m for measurement.
Okay.
And you can confirm that down below, because the only place it's used is this line 59, where which is the line where I'm computing the density of the observation y given this estimated state x tp. And here's where that isNA function comes up. So this is looping through that matrix of observations, but if there's a missing value, it just ignores it.
So that's essentially measurement error.
Yeah, that's the variance of measurement error.
Yeah. And then the x0_p vector. Yeah, so there's a bunch of ways we could have done that, but that's sort of like the starting value for each. If you've got a time series model, you need typically you've got a recursive equation for like next year given this year, but you also have some equation for the first model year. Okay. I'm just wondering what exactly that means. So x0p is just a parameter representing sort of the average, the expected. I mean, it's kind of a stupid way to parameterize it, but it's just the way I did it. That's fine. I was just trying to make sure I understood what it was. Totally. Yeah.
And then the loading, the LP is the Cholesky, the lower triangle, hence the L, or sometimes you can think of it as a loadings matrix in terms of factor analysis. And that's the Cholesky of the covariance matrix, such that epsilon TP has a covariance of L times its transpose, even though delta is a bunch of IID standard normals.
I have like a TMD question.
Yeah.
It doesn't take too long. I feel like I have like a sense for why you would declare delta TP and LP as parameters, and epsilon you kind of like declare as some like transform variable. There's various how we think about it in STAN talk, like transform parameter or something like that.
Yeah.
But why again would you, can you like explain more as why like those two things are parameters and the epsilon is not considered a parameter, just like kind of initialize it later on?
Yeah, so I could have built this, so again, next week is when we'll get into multiple parameterizations of the same model. And a person could have parameterized this model where epsilon is a parameter and just not calculated delta. And that might have been more or less efficient.
I guess my question more is like, can you explain again, like when you declare something as a parameter, like in TMB, how is it treated differently than something that's not?
Yeah, so a parameter, anything in this, anything that's declared as a parameter with that caps lock parameter or something is a parameter that it's expecting on the R side, and that means it's going to try to optimize the model with respect to those parameters. And so, like for instance, if you had a parameter matrix of delta TP and an epsilon TP, it wouldn't really make any sense because in this case, epsilon is being calculated from delta. So, given a value of epsilon, delta is known. So you couldn't have them both be parameters.
It'd be redundant.
Yeah, be redundant. I don't know what the code would look like, but it wouldn't make any sense.
Okay. But can you still do an AD report on something?
Totally. Yeah. So you could AD report out the epsilon TP and get the standard errors on those or whatever, and compare them with the process errors that you used to generate the data if you wanted.
All right.
And that'll be using the delta method to get the.
Yeah, I mean technically, like epsilon is a derived quantity that here I'm using to calculate XTP. So XTP being the states. And so in this case, I think XTP is the most interpretable kind of derived quantity. And so down below, I AD report out the XTP instead of the epsilon TP. Given that we're doing it that way, well, we can look at the parameters. That's not that interesting. We do the Newton step, and so we end up with all the final gradients being less than 1/1,000,000th. And when we do that, we can get these predictive intervals that from the delta method that have sort of some intuitively desirable features. So I don't know just looking at these, I mean, I know the blue's a little hard to see here, but any features of these forecast intervals from year 100 to 120 that seem like they're sort of useful features?
I think it would be interesting to see, back to like my earlier question, the point where the uncertainty around the forecasted predictions stops increasing, because we're saying that that's kind of like the difference between being able to estimate, like there's like some like point where the variance is going to get bigger.
Totally. Well, and it comes back to the stationary thing. So this model is a random walk, and so the variance of the random walk process as time goes to infinity, the variance goes to infinity.
Oh, okay.
And so in this case, the variance will increase infinitely. And here we're plotting the standard, we're plotting standard errors at the square root of the variance. And so it's kind of increasing in this sort of, it's increasing. It will increase forever, but the rate of width of that standard error is, there's a term for it. The standard error squared is increasing linearly with time. Any other stuff just looking at these forecast intervals that looks like kind of useful features?
It's gonna be harder to predict stuff that's, or forecast stuff that's a bit more variable.
Yeah, right. So the standard error, the forecast is getting bigger as you go forward in time. The forecast interval is wider for the populations that have higher variance. So population 5 and 3, it looks like, have higher interannual variance than population 1 and 2. And so the model's able to capture that and use that information in the forecast.
It also looks like there's some like AR process maybe.
Well, right, we know from the data, I mean, we know because we simulated it that there isn't, but it's interesting because they're all positively correlated, all the time series, and so like population 5 and 3, you can kind of squint and see that they both start going down again in year 20, year 80. And population 2 also goes down year 80. So like, you can start seeing sort of the correlation between populations.
Oh, and the predictions you got from appending those NAs, is that what?
Yeah, well, exactly, yeah. So the code was set up where the vector of states, or the matrix of states, XTP, has the same dimension as the matrix of data, YTP. And I passed in a matrix of observations with a bunch of NAs for those years 101 through 120. So what would happen, what do you hypothesize would happen, say, if you had if population 5 had no data for year 20 through 80, how would that look different? The forecast intervals look different for that population?
Would it be sort of like a slope between the year 19 and year 51 or something like that? Would it be like a straight line almost?
Yeah, so the mean of the prediction would just be a linear slope between them. And also, what about the standard errors? Yeah, they'd be narrow at the sides and balloon out in the middle. And we can show that in a second. And then, in terms of the true values, if we plot the true values in the black lines, a 95% interval like we're showing here includes, the true value most of the time. So that sort of, by eye, looks plausible in terms of the width of the forecast interval. But, the final step that we haven't really talked much about is, I just saw like a grumpy paper. I think there's like a grumpy paper every year where people are like, oh, people use AIC to select among models, but then they never actually show if the model you selected is any good. And so, which is like a good thing for Tim. I mean, if the Tim's lab wants to write a similar paper. So one way to evaluate whether your selected model is any good is to simulate data, inspect residuals, or conduct a simulation experiment to see if you end up, if you simulate new data and from your fitted model and fit the model again, are your predictions from that centered around your true values, centered around your original estimate, sorry. So like that's a method that in fisheries, Mark Molitor and Wei-Hua Li recommended that as a diagnostic for estimates of steepness and stuff. I forget why I started using red, having red up here. The next thing I wanted to show today was the code for how to use this new feature in TMB called simulate. So yeah. So far we've focused on, well, okay, actually, I'm sorry. I just wanted to show a little bit more on the R side about how we did that, that model we just looked at. So we've got a parameter matrix, parameters LP, that looks like this, where, but the parameters are, currently parameters is the full matrix instead of just the lower triangle part. And if you try to estimate the full matrix, you'd have P times P, or P squared degrees of freedom, whereas the covariance matrix only has, has fewer degrees of freedom than that number of parameters. And so some of that would be redundant and Hessian would not be invertible. And so, one way to deal with that is to just put in the map argument to turn off. Turn off a bunch of elements. So in this case, map is NA for all of the upper triangle parts. And so if we do that, we end up with, let's see, table names obj_r. We end up with 21 elements of LP that we're estimating, and that makes sense because that's the number of degrees of freedom of a 6x6 covariance matrix. Okay, so next we look at this multivariate Kalman with simulation. And
Wait, can I actually really quick on these?
Totally.
Sorry.
Yeah.
So in your TMB code, when you loop through the calculating the epsilon from the Cholesky.
Yeah, I don't know which way to say it. Yeah.
I think I've heard both. So.
Yeah.
Do you loop through just the lower part of the? Because it looks like you do for every. I guess maybe I'm just not following like how the loops actually.
Yeah. So I think the way that this loop is working is it's looping through the whole matrix, not just the lower triangle part. And so I'm kind of wasting some computational time because I'm defining the matrix to be lower triangle where all the other elements are 0.
And then just because you said this is, you mapped the upper triangular, even though
to be 0.
You're like it tries to estimate it, but then it's like, oh, you said not to like.
Well, no, it's just defining those elements to be 0 so that the starting values of parameters, LP, all of those upper triangles are 0s and they're turned off at 0. So the model will never change those values, they'll just always be 0.
Right.
And I think what you're pointing out is that this line could have been done more efficiently where either P1 or P2, instead of going through the whole row, I could have just gone through the non-0 portions of it. Sure. So this code could be optimized to work a little faster. Yeah, so this model is otherwise identical, except it now has this block called simulate, and I've never really used this except in this homework, or this example. So this was sort of a fun excuse for me to learn a new feature in TMB, but then you can read more at this URL. But it's basically a way of defining how to simulate data in your C++ file. And I think that's useful because you could make sure that your simulator is built in at the same time as your estimation code. And so it's easier to check for bugs, basically. You can, instead of having a simulator that's written in R and that's, using totally different subscripting and notation, you could just have your simulator built in at the same time as your estimation model code. And it's probably a little easier to maintain over time. Although again, I've never used it extensively, so I don't really have any strong claim about it being easier in practice or not. But the way it works is that essentially you just simulate new values that overload any parameters that you want. And so in this case, delta TP is a parameter, but I'm just overwriting it, when I simulate data, I'm overwriting the inputted values based on the the distribution that I know about that that parameter.
So you're pretty much changing the initial values using this sim function.
Yeah, the simulate is just generating new values for that delta TP from a standard normal, because that's what I'm going to treat as later.
You're still fitting the parameters in that.
Well, no, so it's not going to, so the simulate stuff is totally different from any estimation, and all it's going to do is output a new data set. In this case, it's going to output a new data set YTP, and we can see how that looks on the R side.
So this is for like doing your predicted check part?
Yeah, exactly. So maybe we can look at the R side first. So if we, what we're going to do is we're going to run the model one last time. And just as a note, this model runs pretty slowly because it's not a separable parameterization, and we can show that in a little bit. So in this case, by trying to make sure that we didn't have to invert a covariance matrix, we ended up with a parameterization that worked really slow for the Laplace approximation. And so in fact, we would have had a faster model doing a different way of parameterizing it. We can talk about that next week. And if you ever want to see the sparseness, the separability, you can check the sparseness of the Hessian matrix by doing the obj and SP Hess function. And in this case, I guess it's dense enough that it's taking a long time to plot. So what this is saying is that out of the random effects, there's a few random effects that are sparse, I think, and then there's a bunch of blocks of random effects that are totally dense. And so every one of these black, it's pretty funny looking actually. I guess maybe the predictive parts are all sparse, and then all of the parts with data are all dense. I don't know what I would have expected about this, but clearly like the black is the parts where the Hessian is not zero, and there's huge parts of this Hessian matrix that are non-zero, which will be really slow. So if we do, I'm not going to do the whole simulation experiment. We can look at the results I did when I ran it overnight, but I'm going to make a matrix of simulated parameter estimates. So simpar, I'm going to do 100 kind of parametric bootstraps where I simulate a new data set given an NLE for all the parameters, and then I refit the same model and I record the parameter estimates again. And if the model is well behaved, all of my estimated parameter estimates from this bootstrap should be centered and normally distributed around the values from the original model. And that sort of falls out of the claim that the model is. That's sort of how you can check consistency of your parameter estimates, or unbiasedness of your parameter estimates. So if your estimates with these parametric bootstrap replicates are not centered on the original value, then it indicates your original model was likely to be biased.
So you fit the model to your data,
Yeah.
you get the parameters, and then you're using that same model that you generated the parameters from to simulate new data.
Yeah.
And then you fit the same model to it again.
Yeah, record those parameters, and then compare the set of bootstrap parameter estimates with the original parameter estimates. They should be centered on those original estimates. And Hans Skaug has claimed to me that difference between the estimates in those bootstrap replicates, the difference between those and the original parameter estimates is a measure of bias, expected bias. But I actually don't know. I haven't seen that bias used as a bias correction algorithm. He says that you could use that as a bias correction algorithm, but I've never seen it. Okay, so I'm not going to do, like I said, I'm not going to do the whole simulation experiment because it would take too long, but I can show you how to simulate the data set using the T&B approach, and that's using this new function called simulate in the T&B object. And if I do that simulate function, it works really quickly. I get a new simulated data set. And it's just reporting back everything that's been reported out of the model. And so it's reporting back cov pp and var m and xtp and epsilon tp and lp. But I've also got this report statement in the second block of simulate where I generate data given the simulated states. I've got this report statement here. And so it also reports out OITP here. And if I look at the top of it, it's not the same as the original, data. So it's sort of plausible that it's doing what we think it's doing.
So you only had to simulate one parameter, and it estimated the rest based on that one simulated parameter.
Say it again?
So in this top block for simulate, you simulated delta TP,
Yeah.
but you didn't have to simulate any of the other parameters.
Yeah, exactly. So what I'm doing is I'm simulating it. Well, I'm actually not entirely sure. I think what it's doing is it's simulating new values for all the random effects and not the fixed effects. But we could look it's been a while since I put this code together. Maybe this is why you don't teach a function that you haven't used very much. Well, I would have to read through this block of instructions to answer your question very well. I don't know. I don't think. Let's see. I'm almost positive that it's just taking the and this makes sense from how we were talking about it before. So it's taking the maximum likelihood estimates of all of the parameters that we estimated. So I'm giving it as the parameter values. I'm giving it the estimated values of all of the parameters, fixed effects and random effects. And then I'm telling it to simulate new values for the random effects, given the fixed effects. And so in this case, the only random effect in the model that I've declared is delta TP. And that's shown up here, where I define random as delta TP. And so to do a parametric bootstrap, I want to simulate new values, the random effects, but leave all the fixed effects at their estimated values, and then re-simulate the data given the fixed effects and the random effects.
Wait, why do you want to simulate new random effects? Why not just?
Yeah, you could do a parametric bootstrap, I guess, where you just leave the random effects at their empirical Bayes predictions. But I think that the model is sort of treating them as random, just like the data are random. And so, you simulate new values for them.
If you left them fixed, would the only random thing
would be,
change would be the measurement error.
yeah, exactly. And I don't think it'd be that interesting as a simulation experiment. It's true that I'm not sure. I mean, you could also do a simulation experiment where you simulate new values of the fixed effects from their estimated standard error matrix, you know, the matrix of the estimation matrix. And that could also be an interesting exercise. But I guess what I've seen Casper Christensen do is just simulate new random effects and new data. And he's been advocating that as sort of the most interesting diagnostic for checking, you know, the biasness of your model.
So can we walk through this part again? So before you get to the loop, you optimize it, you get the MLEs.
Yeah.
And then in your simulation,
Yeah, it's funny syntax the way he did it on the C++ side. But yeah, we keep going.
so SimPar is just, it's a matrix that's going to hold the results of your estimated values. SimData, simulate. So that part is actually what TMB is doing, simulating the new data set part.
Yeah, exactly.
So are you taking the data set that it simulated from the previous run and then putting it?
Yeah, exactly. So I'm simulating a new data set using this obj $simulate function that on the C++ side is simulating a new set of random effects and a new data set, given those random effects and the MLE.
And that's the MLE part is the obj $, and $last.par.
Yeah, exactly. And for some reason, the way he built this, he wanted the parameter estimates for the fixed effect, for the fixed effects and the random effects.
But because you have that simulate the delta t's, for that matrix is in the code, it's actually also going to it's going to simulate new random effects.
Exactly. So it's passing a bunch of values for delta in this last par. Table named. So last par includes 720 values for TP, which makes sense given that you've got 120 years for 6 sites. But the C++ code is immediately overwriting those, when you do the simulation, is overwriting those values with a new value simulated from a random normal distribution.
Right, okay, so then that you do in the second line.
So it replaces, yeah, sorry.
No, it's okay. And then you actually do the next fit.
Totally. So I can build a new object called obj2, and then I calculate estimate the MLE for that new data set, and save the parameter values. And then because it was slow enough, I would just print a message to terminal every 10 replicates just to keep track of the progress.
And so then when it goes to the next loop, right, it's going to go back to your original obj.
Exactly,
Yeah,
because it's not overwriting the obj. Yeah, and again, I mean, so it's passing in all the best parameter, the fixed effects and random effects. It's overwriting the random effects. It's using them to calculate the states for those new random effects. And it's simulating new data given those estimated states, or simulated states, reporting that out. And then, there's a bunch of extra slots in the SimData has a bunch of different slots, and all this make AD fun is expecting is the SimData YTP, really. So I could have just done YTP, I guess, here. And that would just extract only what it cares about.
Just because those other things are already set.
Well, those other things aren't expected in the C++ model doesn't even know to look for them. The only thing that's defined as a data input is the YTP. Whereas sim data has YTP plus a bunch of other junk that it's just ignoring. Well, I don't mean to get too hung up on the simulate feature in TMB. I think this is the only time that I'm gonna bring it in. But it seemed like something that it's worth people knowing that it exists, but if it's not intuitive, then
Is
there's
it
no.
slower than simulating a new data set each time in R and feeding that in?
I think they're probably equal speed.
Okay.
But I'm not sure. And it's using it's using random number generators in C++. So as Elizabeth said, maybe there's some worry about that that I don't know about. Like I said, I think the only reason to do this is if you've got a really complicated model, you want to develop your estimation model while simulation testing it. I just think that's the normal workflow we all need to be doing. And the claim is that this is less error prone. It's more robust to human error, user error, because you've got the simulation code sitting side by side with your estimation code.
No, this seems awesome.
Yeah, I think it could be useful for some stuff. Yeah. There's also a function called check consistency in TMD that I haven't bothered to start exploring yet. But it uses simulation code. You can only do it if you've defined a simulator, and it's still in beta, so I just haven't started exploring it yet. Okay, so we're almost out of time. When I ran this experiment with 100 replicates, I got this for the result, where red is the histogram for every parameter value and black is the true, the MLE from the original run. And the ones that probably matter the most are these ones. These LPs are kind of squirrely because, well, first of all, they're defined only up to a negative. You could make all of the, you could make a whole, how does this work? You can make a whole row of the Cholesky positive or negative multiplied by -1, and it doesn't affect the covariance matrix because you're multiplying all together. And so in some cases, like there's, estimated a negative number where it's a positive number. But all of the other parameters look well-centered. And so I think the claim is that this is doing okay in terms of simulation testing.
I had a question about I think like, as far as like how the model works, it makes sense why you have a random effect for the delta TP, but is there like a way, like an intuitive way to explain like why that's necessary? Like why is like,
Wait, why what's necessary?
I guess I still don't really have like a sense of like what that delta TP parameter is. So like why do you need a random effect on it?
So delta TP is used to calculate epsilon TP, which has active covariance.
Mm-hmm.
And then epsilon TP is used to estimate the state's XTP.
Mm-hmm.
And the model, of course, is trying to estimate XTP. So that's why you need delta TP in the model, is it's just sort of the way we're generating the transitions in XTP.
And so it carries up a random effect to like the XTP.
Yeah, so XTP, you could parameterize it in at least two other ways now that we're talking about it. So one of them would be to not use delta TP and just make epsilon TP a random effect, where every row of epsilon TP has a multivariate normal density function. Or you could make XTP a random effect and not calculate delta or epsilon. And in that case, epsilon, X would be a random effect. It would be itself. I might have a slide where maybe this is relevant. So again, we're going, the top line would have X, XTP is on the left-hand side of a tilde, and so it's a random variable. And if you coded up that first line directly, you would have XTP be a random effect. The second line, the second block of code has epsilon be a random effect that's zero-centered. And so you'd have epsilon be a random effect. The third line is a third parameterization where you have delta be a random effect. And then you calculate epsilon as the Cholesky times delta.
I see. Just kind of.
And so they're all different.
Levels.
Yeah, they're all different parameterizations in the same model.
Yep. That clear. That's like exactly what I was talking about. Thanks.
Yeah, and again, like we'll see next week, the different ways of doing that have implications for the sparseness of the Hessian matrix. So if you calculate if you coded up the model those three ways, you would get the same MLE all three ways, but the SP Hess function would show that the Hessian looks really different. Okay, so that was all I wanted to cover. We only have 10 minutes left, so yeah. So the exercise I was going to do was basically about using what I've been calling in my own work a trimmed Cholesky. So if you take a Cholesky matrix and you don't have you zero out some of the columns, you can have fewer parameters to estimate. And so you can, and that's sort of like interpreted as a factor analysis decomposition. So like Eli Holmes and Mark Sherrill and Eric Ward use this all the time in their Mars package, and I use it in my spatial dynamic factor analysis. So in that case, you could code up L being fewer columns than rows, and then make it full rank by just adding on a diagonal matrix, and still have fewer parameters than the full Cholesky decomposition. But I don't think we have time to do it. So, but if you're interested, feel free to try the exercise out later. Any remaining questions or? Okay, so homework 3 due on Tuesday. I was gonna grade homework 1 and get it back to you this week, which is, after anybody, nobody'd get credit if they turned it in now anyway. But because I'm sick, it might be a little late.
Thanks, Jim.
Yeah.
Wait, Jim, for in the C++ code, you could just have this function that just says .row 0. Does that just give